Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics, and we are going through this particular paper, namely physics of materials, and now we begin the new chapter on band theory of solids, and this will be the first lecture in the band theory of solids. Now, as students of electronics, you should know valence band and conduction band. You know this kind of valence band and conduction band, they do not exist in metals, but in the case of semiconductors, you have electrons residing in what is called a valence band, and then the conduction band, there will be energy gap. And in the band theory, the motive or the main objective is to make you to understand how one is able to explain or arrive at the kind of bands I am talking about, a collection of electrons, the so called valence band, and then again a collection of electrons residing in the conduction band. Let me ask you at this point a fundamental question. Do you have valence band and conduction band in atoms or molecules? You take a hydrogen atom or you take a sodium atom. Have you heard of valence and conduction bands? You have only discrete atomic levels, you know, in the case of atoms and molecules. Only in the case of solids you have valence band and conduction band. Now, before we proceed further, let us now have the contents of this lecture. The contents are as follows. Let us now try to go to the elementary principles, elementary things like the periodic table. Then the most of this lecture will be to review the free electron theory, in a review of free electron theory and Sommerfeld's model of a metal, the quantum theory, right, Sommerfeld's quantum free electron theory. Now, these are the things that we will be having in this lecture, and this lecture should be dedicated to those people who are responsible in proposing these theories, the theories for how electrons behave, how one can explain conductivity in a metal. We will not be talking about semiconductors. The main objective of this chapter is ultimately to have a better understanding of semiconductors, but first of all we will have to have an understanding as to how you explain the movement of electrons in metals, and that too simple metals. It was started by Paul Drude. It is called the Drude-Lorentz theory. You got a Drude here, and you have Lorentz, and you have the Drude-Lorentz theory. What does that theory do? It tries to explain the electrical conductivity in the case of a metal. You know how electrons flow in the case of a metal. That is what they try to explain. That is what we will be trying to do, and then we pass on to the Sommerfeld quantum free electron theory. What is the difference between the free electron theory given by Drude and Lorentz and that of Sommerfeld? As I told you, Sommerfeld theory is called the quantum free electron theory. This is a classical free electron theory, right? What is the difference between classical physics and quantum physics? In classical physics, what was done by Drude and Lorentz is to treat the electrons as gas molecules. You have the kinetic theory of gases, which you have studied in the high school. You know the gas molecules are moving, they are colliding, and similarly all the attributes which were associated with the molecules were attributed to the electrons and metals. That is what was done by Lorentz and Drude, the Drude-Lorentz theory. And you know the electron was discovered by J. Thomson, and one knows that the movement of electrons gives rise to electrical current or the conductivity. Okay. The conductivity is nothing but the movement of electrons. When you apply you have got a metal, when you apply a electric field, you have got a positive and negative, you have got a battery. In a metal, this is a positive and this is a negative. Then if you have got electron being negatively charged, it moves towards the positive end. That is the so called movement of electrons in a particular direction. The conventional current is supposed to flow in the opposite direction, right? The conventional current flows in this direction. Now, these electrons were assumed to behave something similar to the gas molecules by Drude and Lorentz, and that is the reason why it is called a classical free electron theory. So, in the periodic table, what you understand is you have lots of metals which are shown by this color, right? This color shows metals, and they are the non-metals. You got you know very well that you have silicon and germanium. There are diamond or carbon. There are non-metals. You got non-metals here, right? You got non-metals. Now, the theory which is advanced by Drude and Lorentz, they cannot be applied, and you do not intend to apply for non-metals. You are concerned only about the metals, how the electrons behave in the case of metals, and so we are confining ourselves to this region. In this region, let us take the example of sodium. You know, sodium is a good metal. Why do you say sodium is a good metal? As of today, you use liquid sodium as a coolant in nuclear reactors. The heat generated in nuclear reactors, the heat is removed by sending liquid sodium. Liquid sodium is used as a coolant, right. Sodium is a good metal, right. Sodium is a good metal. Now, so magnesium is a metal, beryllium is metal. So, we are confining ourselves to the metals, as was done by the theory is only for metals, the theory given by Drude and Lorentz. Okay, we are, so as I told you, we are looking at the sodium atom. What do you know? You know, in the periodic table, sodium forms the first group, right. This is the first group, the second group, right. You know the meaning of group and all. They have got similar physical and chemical properties, right. The valency of sodium. What is the valency of sodium? In the first group means valency will be 1. Where do you have the valence electron? You have to look at the whole of the atomic or electronic configuration. the number of electrons that you have in sodium is 11. The atomic number of sodium is how much? It is 11. So, what is electronic configuration? Even in high school, you know, you would have studied, you write the electronic configuration as 1s2, 2s2, 2p6, 3s1. Now comes the important thing, namely these electrons that you have got here, the 1s2, 2s2, 2p6. Now the 3s, how many electrons you can have? You can have 2 electrons here, but you have got only 1 electron here. Now, so these electrons are in the closed shells, right? You got 2 electrons here, the 1s2, then you got electrons here, and you see them 3s1, that is a lone electron in the outermost shell. That is important. There is only 1 electron in the outermost shell, that is called the valence electron. Now you should distinguish between core electrons and valence electrons, and also to understand the distinction between core electrons and valence electrons. Now I want you to focus your attention to this one, 1s2, 2s2, 2p6. These electrons are called the core electrons, right, and this is the valence electron. Now what is the role of the core electrons? I mentioned 1s2, 2s2, 2p6, they are the core electrons, 3s1 is the valence electron. What is the role played by core electrons? What is the role played by valence electron? Now the core electrons do not play any role in deciding the physical properties as well as chemical properties from closed shells. You know, the 1s2 is a closed shell. You got the 1s orbital can have only 2 electrons. The 2s2 is again a closed shell, it can have only 2 electrons. The 2p6, that is subshell, can have maximum 6 electrons. They are the closed shells, and what I am trying to tell you is the electrons in closed shells do not contribute anything to the atom, or in other words, the physical properties as well as the chemical properties are decided by only the valence electron. I told you that they do not contribute, the core electrons do not contribute anything to the atom. That means the properties, the physical and chemical properties of atoms are decided only by the valence electrons. This is the important point. You may ask me why. The question is what about the core electrons? Why they do not play any role? The reason being, you take the magnetic quantum number ml, and similarly magnetic spin quantum number is the orbital. L is the orbital quantum number, S is the spin quantum number. The net resultant of ml, the resultant magnetic quantum number ml, and similarly the spin also you take the resultant, both of them will be equal to 0. For instance, I take the p shell. For p shell, what is the L value? L is 0, it is called S state. For a p state, L will be equal to 1, right. L equal to 1 means it is a p state. What are the ml values? Ml will take 2L plus 1 values. What are the ml values? Plus 1, 0, minus 1. If what is S value? S means spin. Spin is equal to half. What are the ms values? Magnetic spin quantum numbers, plus half and minus half. If you say that S is equal to half, what is the physical meaning of it? You say the electron has got a spin half. What is half means what? It is half a rupee, of $1. What is the meaning of the statement? The electron has got a value of spin, the spin value is half. Half means what? You know, you should know the spin angular momentum is half h bar. What is h bar? H bar is the unit of angular momentum. How do you understand all these things? It is Niels Bohr, he gave the postulate mvr is equal to nh bar or nh by 2 pi. The angular momentum electron is revolving with the proton at the center. He took the hydrogen atom, Niels Bohr took the hydrogen atom as example, right, the simplest atom to be dealt with. The proton will be at the center, okay. The lone electron will be revolving in a orbit, right. So, he made the postulates. One of the postulates says that the momentum associated with the electrons when they are found in different orbits should be equal to mvr is equal to nh bar. The angular momentum mvr should be integral multiple of h by 2 pi. H by 2 pi is nothing but h bar. So, mvr you find on the left hand side, the angular momentum. Angular momentum should be integral multiple of something. That something is the unit of h bar is the unit of angular momentum. So, when you say electron having a spin half, the meaning is the spin angular momentum or the angular momentum coming from spin is half h bar. Is it all right? The meaning of your, when you make a statement, the electron has got a spin half, the meaning of the statement is the spin angular momentum which one can associate with the electron is equal to half h bar, right. So, for a p shell L is equal to 1, what about sigma ml? As I told you, ml will take 3 values +1, 0 and -1. The summation of these 3 values, that is sigma ml will be +1, then +0, then you add -1, right. That I am putting inside the bracket, that becomes equal to 0. What is the meaning of that? The resultant orbital angular momentum is equal to 0. The electrons in the p shell, the resultant angular momentum, orbital angular momentum will be equal to 0. And similarly, for the electron which has got a spin half, the magnetic spin quantum numbers will be half and -half. So, the sum of these two will be equal to again 0. Okay. So, sigma ms also will be equal to 0. The magnetic spin quantum number, the resultant magnetic spin becomes 0, the resultant orbital angular momentum also will be 0, the resultant orbital angular momentum, the resultant spin momentum, all of them will be equal to 0. Therefore, the magnetic moment associated with the electrons which are found in the core states, they are core electrons, right. They are core, they are the electrons residing in the filled shells or filled subshells. Therefore, the electrons in the filled shells or subshells do not contribute anything, right. That is the reason why you are concerned about valency. Sigma ml and sigma ms, both of them, they become 0 for closed shells. Therefore, whatever momentum or whatever magnetic moment that the atom will have comes from the valence electrons. Therefore, one should understand even at the beginning, any student of material science or applied electronics student should know the role of core electrons and valence electrons. What I am trying to tell you is only the valence electrons are of importance, because the core electrons do not contribute anything, right. Sigma ml is 0, sigma ms is 0. So, the core electrons do not contribute anything to the atom or the physical properties. The physical properties are decided by only the valence electrons. So, that is the reason why the elements are grouped together. Now, you should understand you have got a first group. What do you mean by first group? The valency of all the elements residing in the first group, the valency is 1, right, the first group. They have got, why are the group? We should attach the name group. They have got similar physical and chemical properties. Look at this last column: helium, neon, argon, krypton, xenon, radon. They are called inert gases. Why do you say they are inert? Because they have got, what is the electronic configuration? S2p6. That means they do not have any valence electrons at all. Valency is 0. That is the reason why they do not react chemically, they do not react, and they are inert. So, these are inert gas atoms. Here the valency is 1, right, irrespective of the atomic number. The point to be noted is, it is not the atomic number that is important. It is not the number of electrons in atoms which will decide the properties. The important thing is how many electrons are found as valence electrons. The valency is important. The elements which you find here in the first group, they will have similar physical and chemical properties, right. Then you can take copper, silver, gold, the noble metals you got, right. Copper, silver, gold, they are called, why are they called noble metals? Because the properties are again similar. The second group, so elements beryllium, magnesium, etc. will have similar properties. So, the properties are decided by the number of valence electrons. That should be very important, right. And again, there is time for the students of electronics to know where you find silicon, because most of the semiconducting materials are silicon based. Some of them are germanium based. You know very well, up to 1960, germanium played a significant role. After 1960, most of the semiconducting components are made up of silicon, right. Silicon based transistors are important. Again, silicon solar cells are important. Okay. So, you should know the valency of silicon and the valency of aluminum, phosphorus, and so the third group and fifth group, this is the fourth group. The silicon, germanium, they form the fourth group element. This is incidentally I am telling, I will come back to this once again later. And now, so the valence electrons only decide the properties. That is the thing that should be borne in mind by all the people who are studying about atoms, right. Only valence electrons decide all the properties. All the property means thermal, electrical, optical, all the properties are decided by the valence electrons. Okay. So, the core electrons for sodium is you got 10 electrons, the valence electron will be only 1, and the important thing to remember is these 10 electrons do not play any role, and only the lone electron plays the most important role, because that alone decides the physical and chemical properties. Okay. Then the electrons that you have got, they will be according to Sommerfeld. What about the free electrons? In atoms, the electrons are free, right. The electron is here, it will be revolving like this, right. When you combine 100 sodium atoms, right, you combine the atoms. Now, what will happen to the electron? Will it remain, will it be attached, or will it remain with the atom? Actually, really what happens is, if you bring 100 sodium atoms, you know very well sodium is a metal. That implies, that means what? You should be having free electrons. If you do not have free electrons, how will you explain electrical conductivity? Only the electrons should move. If these electrons are intact with the atoms, when you bring 100 atoms, the number of free electrons will be 0, because every electron is associated or kept intact with the atom. So, if you bring 100 or 1000 atoms together and form a solid, then the point is the electrons will take part in conductivity will be 0, because you do not have electrons, right, to carry the current. What is current is nothing but the flow of electrons, right. Flow of electrons means there should be electrons to freely move in a particular direction. And where from you get these electrons? These are the electrons which you find in the outermost shell, the outermost orbit, outermost shell. These electrons will become free. When you bring 100 sodium atoms together, the because the valence is 1, there will be 100 free electrons. What Drude and Lawrence did was to make use of kinetic theory principles and treat the electrons like gas molecules, right. You know, you have studied kinetic theory of gases, wherein you have obtained an expression for the pressure of the gas. You write P is equal to 1/3 nmc square bar. These things you have studied at a lower level. Pressure will be 1/3 of nmc square bar. What is c square bar? The mean square velocity of the molecules. The molecules are moving in a gas, the molecules will be moving here and there, right. They will be moving and they are colliding with each other, and you would have heard of or talked about mean free path. What is mean free path? the distance travelled by a molecule between two successive collisions. So, you treat the gas molecules as billiard balls. You can visualize number of balls moving here and there, they collide and then it travels and then it collides and so on. When you do not apply any field, the balls or the electrons will be moving freely in all directions. The gas molecules will be freely moving in all directions in the according to kinetic theory principles applied to a gas. Similarly, the electrons are treated as on the same footing. That is the reason why it is called a free electron gas, because whatever ideas that we had for the gas molecules and those at those years, whatever ideas that we had with regard to gas molecules were applied by Drude and Lorentz to the electrons also, which should not be the case, because electrons are charged, whereas gas molecules are uncharged. They will be moving here and there, they can collide and so on. But remember, electrons are charged particles. Not only electrons are charged particles, at this point of time you have studied about Pauli principle, right, the spin and so on, because I told you about spin, the Pauli exclusion principle and other things come into the picture. Therefore, the electron should be treated in a different manner, but at that time when Drude and Lorentz started to explain the electrical conductivity in metals, the flow of electrons or the flow of how the current flows in a metal, what they did is to treat the electrons as gas molecules. They will be randomly moving and colliding, like as in the case of gas molecules. So, the free electron theory of metals, you have the animation shows the electrons moving here and there, they collide with each other, and similar to the mean free path, between two, it will collide with an ion, okay, then it will collide with another ion and so on, right. Now, this is a static picture. You see them, what happens now? You have electron here, you follow the path, the electron goes and collides with the ion, right, because the electron has been stripped from the atom. So, what happens to the atom? Atom will become a positive ion, right. When you out of 11 electrons of sodium, if one electron is removed, then there will be 10 electrons and 11 protons. So, 11 protons and 10 electrons means it is a positive ion. There is one excess proton. So, you got a collection of positive ions. Is a metal. How do you visualize a metal? It consists of positive ions and then lot of free electrons, right. If you got 100 sodium atoms, bring them to form a metal, then what you end up with 100 positive ions and 100 free electrons. Now, we are studying the movement of free electrons. According to Drude and Lorentz, what happens is the electron goes like this, the electron E minus is a charge, negative electron is negative charge, that was found by Thomson. All these things all of you know by now. The electron goes, it hits the ion and then it moves in this direction, it hits the second ion, then it travels in this direction hits the another ion, then it goes in this direction. When you do not apply an electric field, what will be a current? You got a metal, you do not apply any, you got a metal here, right. You do not apply, you consider this is a metal, right. You do not apply any electric field. In the absence of the applied field, the electrons will be moving randomly. What will the current? The current will be 0, because you are not applying any field. So, the electrons are moving in random direction. So, the different electrons will be moving in different directions. So, there will be the electrons which are moving in a particular direction, the resultant current will be 0, right. So, it will not give rise to any current. That is what you are seeing here, electron goes here, goes here, goes here and so on. Now, tell me what is the mean free path? How will you calculate the mean free path? Like the gas molecules, the mean free path is the distance travelled by an electron between two successive collisions. You consider the electron here, it has suffered a collision, it travels through a path L1, suffers another collision, then the L2 another collision, L3 the third collision. So, you sum up all the paths travelled by the electron by 3, the number of collisions. The total distance covered by the total number of collisions will obviously give you the mean free path. The words, the terminology which is being used, mean free path. Free path means the free distance travelled by the electron without suffering any collision. It is the so called mean free path. Okay. This is how the electrons are travelling, but when you apply an electric field, suppose this becomes positive, right. You have a battery here, this is positive, this is negative, then the electrons will have a tendency to move in this direction towards the positive pole, right. This is positive, this metal, this end becomes positive and this is negative, then the electrons will try to go in this direction. So, because the electrons are going in a particular direction, that constitutes what is called a current. The conventional current is supposed to flow in the opposite direction. The electrons are flowing in this direction, the current flows in the opposite direction. Okay. That is what you will be having. Based on these ideas, what Drude and Lorentz did is finally to obtain the expression for the electrical conductivity. They are very important expression, the electrical conductivity. So, the conductivity expression sigma is given as the number of electrons n multiplied by short into mu, the mobility. Now, let me go on to summarize what we have learnt in this first lecture. The summary of the lecture goes as follows. Drude attributed the ideas of kinetic theory of gases to the electrons to obtain an expression for the electrical conductivity. This is what was done by Drude. Now, the important point to be understood is take an atom, find out how many electrons are the core electrons. I told you number of times the core electrons do not give rise to anything for the properties, only the valence electrons are important. This is one of the important points, right. Then these valence electrons are treated on the same footing as was done by the gas molecules in the case of gases. How you treated the gas molecules in the case of gases, the same kind of treatment is given to the electrons also. This is what is done. So, this is the basic summary of what we have understood in today's lecture, and you have the following questions. What is Drude's classical theory? And of course, one should know what is the difference between Drude's classical theory and the Sommerfeld's quantum free electron theory. Both are free electron theories, and you have to know the difference. The remaining part that we will be listening to in the lecture to come will be on the quantum free electron theory. With this, we come to the end of this lecture. Thank you.